This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
This is Kanchan Shringi for Software Engineering Radio. Welcome to our show today on training simulator apps. Our guest today is Otakar Nieder. Otakar is Senior Director of Development at Bohemia Interactive Simulations, or BISim. They create training simulators. Otakar joined BISim in 2009. Before that, he worked in the gaming industry. Welcome to our show today, Otakar. It's great to have you here. Is there anything else you'd like to add to your bio before we get started?
Hi, Kanchan. Thank you for having me. It is very exciting to be on this podcast. I think you said all the important things. I'm now the Director of Development in Bohemia Interactive Simulations, where we do these training simulators. And I'm responsible for all the development in all our offices around the world.
Let's get started with an example of a game and a simulation, and then we'll compare and contrast them.
So there are, of course, many games. We can choose from a lot of them. So there are simple ones like Tetris, for example. You might have it on your phone or some other different casual game that you were playing when you were somewhere in a train or bus. The gaming or the simulations, that is a bit more difficult to choose some that would be known to people. So I think that one example is Flight Simulator, which is, I think, somewhere on the border of the games and simulations. It is a pretty good simulator of flying airplanes, but it is being sold as a game on a gaming platform on Steam. So you can buy it as a game, you can play it as a game. But it is also a very, very serious simulator of flying. Of course, on my side, I can put in our simulator, which is called VBS4. It is a simulator that is being used for training military personnel in many different military training cases. There are, of course, other simulations too, especially for some special machinery or, again, flight simulators that are being used to really train pilots. But, of course, there's not as many of them as games.
So what about the infrastructure? Let's talk about the gaming engine. Is there a difference between the engine for a game versus a simulation?
It is a bit difficult question, but I think to be able to answer it, I will a bit limit myself on when I'm talking about game engines. Let's talk about the game engine that you can get yourself, Unreal or Unity. These engines you can just basically get whenever you want, and you may want to start to build a game on that. On the other hand, we would have the simulation engine, which is much more than just the sandbox that you get with Unreal and Unity. So when you get yourself Unreal or Unity, you get, as I said, sandbox and a set of very, very nice tools which you can use to build your game. Use them to create either the 3D content or 2D content. You can use them to create some scripting, some functionality, some interaction. And that, at the end, forms your game. On the other hand, the simulation engine, that is much more. That is something that is already prepared to do some simulation. And again, for the sake of this talk, I will be talking about training simulations. So, of course, you can have different types of simulations of some physics processes or so. But I will be talking about engines that are being used for simulating some kind of a training. And I will be mostly referring to the military training because that's where my expertise is. So if you get a simulation engine like that, you get a lot of functionality that you can start to use immediately to do some of the training. If I should use some kind of analogy, I will use the one that our CEO likes to use. He compares this to the situation when you're buying a log house. Either you can just basically buy a fully featured, fully built, fully equipped log house and move in and be there, or that would be your simulation engine, or you can buy a piece of land, a set of power tools, and a pile of planks, and then you would just build the log house yourself. That would be the game engine that you would just get as Unreal or Unity. So that would be the kind of a difference in how much is already there built to how much you have to build yourself.
We'll drill a little bit more into that in later sections and what is the delta. But before we get to that, can we also discuss how is developing these games or gaming engines or even simulation engines different from standard line of business or web apps?
I think I would like to answer that basically in every game or simulation development, there is a bit of business or web application development, where in the business and web applications development, very probably is not much from the games development. By that, I'm trying to say that creating some bit more complex game is a set of really different kind of things you have to do. You have to think about also a very low level stuff. But if you go a bit higher level, you can create user interface, and these days these user interfaces are often used or often built by using the technologies that are being used to create webs, or like HTML and all of the frameworks that are built upon that. So you have a bit of a web application development there. Games, of course, these days are using databases to store a lot of data that they need about the players and about the characters that are inside. So again, you have a bit of a databases there, which are usually being used in the business development. So I would say that there is a really, like, the gaming is a very complex thing that has a very broad reach of what needs to be done, where I think that business applications might be more focused on one specific thing.
Got it. So the engine is more general purpose. And when you're talking of simulation engines, there are additional features and frameworks and services.
That's correct. The game engine as such is a complex thing where you have to just think about what kind of hardware you use it for and these kind of things. And we can talk about it maybe a bit later. That's similar to simulation engine. But then the more you want to just do and the more you want to train, the more functionality you have to add and the more different, let's say, areas of expertise you have to use and then create the content for the training.
So you hinted at that earlier, but can you summarize the difference between the goals of a game and that of a simulation?
Sure. Like for the game, I think I don't want to just be too generalized, but I think that most of the game or majority of the games, their goal is to entertain, right? To just basically entertain you, to give you some kind of a feeling, to give you something you enjoy. Where the simulation is much more serious, especially when, as I said, as I'm talking about training simulations, it's about delivering training. It's about delivering some kind of skills or training some kind of skills that you will then use in the real life. Maybe in the games, you probably don't have, maybe you do some kind of term of negative gaming, but in simulation training, you have a term that is called negative training. So the simulation, if it delivers to you something that you would then learn wrongly and use it wrongly in your real life, you, for example, in the case of military simulations or military industry, you can cause casualties. Where with the games, it's more casual stuff and more about feelings, where with the simulation, it's more about really training, learning, and delivering some kind of skills training.
So what are the most common industries that invest heavily in simulations?
As I'm working in a company that delivers training simulators for military, I definitely would say that militaries are very interested in simulations. Why? Because simulations save time, they save money, a lot of it, because you don't have to, for example, use ammunition, right? You just basically, simulated ammunition is for free, where the real life is very expensive. It saves paperwork, because if you want to just get out a tank to train with it, you have to fill in a lot of paperwork, where in the simulation, you just basically jump into the tank and you can train with it. So definitely there is a lot of interest in militaries for training, simulated training. But I think I already mentioned, for example, the pilot trainers. Pilots are being trained on very specialized simulators before they actually can go into the real plane. And I see like a surge of interest from other industries also, like the first responders and any kind of industries using very complex machinery that they like to basically train these kind of skills before they start to use the real thing.
So let's now dig deeper into the challenges of developing simulations versus game and the differences, starting with the game engine architecture. So what would you say are the common components or services or layers between gaming engines and simulation engines?
Mm-hmm. So I think that if we start from the low levels, and by low levels, I mean really kind of the levels of touching with the hardware, because that's one thing that is very common when you're creating a game engine. You have to know what kind of hardware you're working with, and you have to understand how the hard drive works, how memory works, how GPU works, how CPU works. And these kind of things that are very common to game engines and simulation engines, because usually for the games and for the simulations, you want to get as much as you want from the hardware you're developing for. So that's where on the low level, the things are very common. I can name here some kind of a component that is interacting with the file system, component that is managing memory, of course, components that are working with the sound cards to create some sounds, and rendering components that are delivering some kind of a 2D or 3D images. You also have to represent your environment or terrain, whatever you want to do in a game or the simulation. Again, that is a very similar component. Of course, it depends on how big environments you want to represent. In the game, you also definitely want to have at least some kind of simple physics. You need to have user interface, and you have to, of course, allow the player or the trainee in the simulation to input somehow to control what is happening in the 3D environment. So again, there is a component for user interface and also a component for digesting the input from different controllers like mouse and keyboard. The other common component would be that you want the user of your game engine or your simulation engine to be able to maybe integrate it with third-party libraries. So for that, you provide some SDKs, some APIs that you can use to do that. And also you want people to be able to create their content. That I don't mean the content now, the 3D content, 3D models. I mean the functionality and interaction functionality. So for that, you usually provide some kind of scripting, some kind of way of how you can program this thing. And probably last but not least, from the very common ones, of course, you need to deliver some tools that will allow your users to either create the 3D content that you want to populate your world with, or some editors that can help you create the training scenarios in the simulation. So these components would be the ones that are very common to game engine and the simulation engine. Without them, you wouldn't have either. But then you go a bit higher level, you go a bit more, offering a bit more. And that's where things start to differ between the game engine and the simulation engine. Because for the game engine, you maybe don't need networking. Maybe you do, maybe you don't. So it might not come as an integral part of the package you get, the sandbox you get. You might need to write your own networking, or you buy a third-party library that actually for that engine provides a networking. Same comes with artificial intelligence. There might be some kind of a very simple artificial intelligence included in the game engine, but very probably you want a different one. So you will have to, again, either create your own or purchase a third-party one. So that, like around these game engines, there is, of course, a lot of third-party libraries and a lot of people and companies that are creating these libraries. Then you can use to enhance your game and to make your game more appealing to your gamers. With the simulation engine, of course, these things have to be there also, but they are very probably more specialized for the training use case that the simulation delivers. So, of course, in our system, we have an artificial intelligence that is very specialized for simulating military doctrine behaviors of different groups of soldiers that are doing different kinds of maneuvers. We focus on also the enemy artificial intelligence behaviors that, again, need to be somehow representing what the soldiers can interact with in the real world. So these things start to be very much more focused and specialized in the simulation engine. Another example would be physics, where, again, in the game engine, you might get some simple physics for calculating collisions and these kind of things. When you want to do something more complicated, you, again, will probably have to write your own. In the simulation engine, you get very specialized, very detailed physics for ballistics or for driving vehicles and all the systems that are actually being there on the vehicles. So these, like basically, when it comes to a more like specialized functionality, that's where the components start to differ a lot. Because where for your game you might need a simple physics, for the simulation you really need a very, very complex physics. Where for the game you might need, when you're creating it for the mobile phone, to operate it with two thumbs. For the simulation, you need to simulate a very complex interaction systems that are representing complicated operating systems for different vehicles. And one thing that actually I haven't seen in any gaming engine, which is actually very common for simulations and training simulations, is something called after action review. It is a system which is basically being used to record everything that is happening during the training and then replay it back. So the soldiers can, or the trainees can just basically look back to what they did and learn from it, and then maybe do the training again and again and again and again, look at the after action review. In our case, this is not a simple video. It is actually, we're recording everything that happens in the 3D environment. So we can replay it again, like exactly how it happened. So you can jump in the 3D environment during the replay, see what was happening. You can pause it. You can see where everybody was, what they were doing, what they were looking at, what they were aiming at. So that is something that I have not seen in games, because you rarely want to return back and replay something so you did better. There are, of course, people like that, but this is something that is very, very like specialized for the simulation cases.
Thanks for that comprehensive answer. So, what I can summarize from that is that you start with a gaming engine. You could start with a gaming engine, which gives you a lot of the components you need, which is, getting the best out of your hardware, the user interface, some of the physics, an input device, SDK scripting. But then you specialize the algorithms, the collision engine, and you further add features to record and replay. Is that a fair summary? And if so, did you guys start with a gaming engine and build upon it?
That's a very good question. It is a good summary. It just, of course, it depends on how complicated your simulation is, and of course, how complicated your game is, because there are, again, simple games and complicated games. The system that we have here in Bohemia Interactive Simulations is a result of work of more than 100 people for 10 years. It's a really, really big system. And did we start with a game engine? Yes, we did. We had actually back then, we started to use a game engine that was coming from the game Arma 2, which was being built by a company, Bohemia Interactive Studio. Back then, we were actually sister companies. These days, we are separate companies. But yes, we have started with a game engine. And I think that in our case, it definitely was worth it, because we got some of the systems, the low-level systems. But then, as I said, we had to spend 10 years of many people working on creating the functionality that then delivers the training and the simulation.
Can we talk about a couple of these areas of specialization? You can pick either the level of mathematics needed or the collision engine and perhaps the use of AI.
Mm-hmm. So when it comes to simulation, I guess that you probably can imagine that if you're teaching people something that then they will use in the real world, the level of real life representation has to be very high. Things have to be precise. They have to really represent real life as close as possible, so you, again, don't get negative training. Because if something would be very easy because not very good physics, then you would learn that it's very easy to do something, and then in the real life you would find out, maybe in a very bad situation, that it is not as easy as it is. So, for example, to repair a tank thread, it's a long process, and if it would just take you 1 minute in your simulation and you learn that it's very quick, then in the real world you would be very surprised what all you have to do to repair a broken tank thread. So if I should talk maybe about the collisions and the physics, that's where we had to probably do the most specific changes or development that usually is not needed in the games. And that's on the precision side, because we are currently having new engine that is simulating the whole Earth. It is rendering the whole Earth, and you can just basically jump everywhere in the world, and you would see some kind of preloaded 3D environment that's procedurally generated, or you can have actually very real world data in there. For that, you then want to just go anywhere in the world from the place where you jumped in. And very quickly, when you're doing the simulation, you find out that the normal numbers, the 32-bit numbers that are being floating point numbers that are being used in all of the engines, start to be very imprecise when you go further and further from the place where you have been. And the physics start to be, which really is relying on the very precise floating numbers, it starts to be very unstable, and out of nowhere you have vehicles that have a small bump fly out to the space, because that's how the floating point numbers are represented in the PC or in the computer. So we had to switch to 64-bit representation of these floating point numbers very early, like many, many years ago, before the games actually even started to think about it. Now, because the worlds are bigger and bigger in the games, they also think about it. But we had to do it very, very early to be able to just simulate all of these vast and big, big environments. So that would be on the physics and collision side. On the AI side, I think I already mentioned that we are specializing on an AI that simulates the behaviors, the military behaviors. So we have to really create a system that can handle that. And because we are not only selling to one army, but we're selling to many armies around the world, which have different doctrines, and they expect basically their artificial intelligence soldiers to behave according to that doctrine. That system has to be like highly parameterizable. So again, that creates it very complex, and we spend quite a lot of time doing it. So these are the systems that we had to just really spend a lot of time on. Another one is ballistics. Of course, if you want to have a realistic behavior of your shells and what they do after they explode, all the particle effects and flashes and these kind of things, you have to spend a lot of time talking to the subject matter experts who will tell you what these things have to do, and then create specific algorithms that can replicate that.
Something you said was very interesting is that the gaming engine is also benefiting from all the work that folks are doing on training engines, training simulator engines, making it more real. So that was interesting to me.
Yes, definitely. Like, I think the simulations are just kind of, at least in our case, we're just pushing what is possible with a game engine, like what is possible to show, what is possible to represent, what is possible to interact with. So I think that we're pushing the boundaries a lot, maybe more than the games, because again, we need to be very near to the real world experience, and where some of the games, of course, try to do that too. They just aspire to that. They want to do that, and if they find out that they can't get too near, they probably are okay with it. They can cut corners here and there. We can't. So definitely, we're maybe one step ahead of the gaming development.
Let's talk about deployment. And the specific question I had at this point was that multiplayer games require cloud-based game service. Is that true for simulations as well? Are there use cases that you have many folks participating in the simulation?
Very good question. I think I forgot to mention it when I was talking about the components, different components of the simulation engine. Training mostly is about collaboration and cooperation. We were saying that our training is cooperative. We do not focus on training one soldier doing one thing on her or his own. It's just basically cooperative training. So, of course, we do support multiple trainees being in the same scenario. So some kind of a multiplayer game. But the difference is that, of course, I think everybody knows about these massive multiplayer online games, which, as you say, need a cloud-based servers, and there are hundreds of thousands of people playing games on them. We, in the simulation area, are much more like restricted and much more focused. So we always have to think about what we are training and what is the benefit of doing something for the training. having 100,000 trainees in the training might not be that good of a training. I'm not sure what exactly we would be training. So currently, we are focusing on hundreds of simultaneous trained people. We are currently having customers who are training with 200, 250 trainees at once. Of course, our customers are thinking about how to make these trainings bigger. They are thinking about, as I said, like how the training would go. Of course, if you want to go into a brigade level, that starts to be thousands of people. So, of course, our customers are thinking about bringing more trainees in, but the more trainees are in, the more logistics problems. So, we at this moment, to return back to your question, we are not having like servers in the cloud, and we're not like leveraging that functionality. On the other hand, our customers are talking to us, and we're thinking about how we can the best actually jump on that, because we know that in the cloud there's a future, and we are thinking about how to use cloud to allow us to improve our training. And it's actually currently not in the number of how many players we can support at once, but it's more for us how many vehicles, really very detailed vehicles with detailed physics we can simulate, and how many artificial intelligence units we can have in one training.
I see. Let's talk about the hardware. You did mention that it is important to get the most out of the hardware. So are there any prereqs that you have on the client hardware?
For us, it's a bit more complicated than for the gamers, or for the gaming companies, because the games usually just come with the best graphics. And for the best graphics, if you want to buy the latest game, I don't know, Cyberpunk, the gamers are like, okay, well, I will buy a new hardware for it because I want to play it on the best details and whatever. We are working more with big agencies, and of course, the tempo of changing the hardware is not as fast as for the individuals. So we have to live a bit in the past. We have to support hardware that is not the top of the shelf hardware. So we always have to focus on not only bringing or creating more complex simulation or more complex environment without thinking about how we always also have to think about, okay, so we want to do this more complex thing, but how can it work on a hardware that is 2, 3, 4 years old? Which again makes the work that we're doing on the simulation side a bit more complicated than for the gaming companies, who can maybe just basically assume that the gamers have the latest hardware.
So you have more constraints.
Yes, we do have more constraints.
What about hardware peripherals? What are required for your simulations? Joysticks, VR headsets, steering wheels, anything else come to mind?
Yes, so definitely a lot of more. I will start with the controllers. Of course, joysticks. Like, actually, some of the training is being done with keyboard and mouse, and basically the trainees are using our software as they would use some kind of first-person shooter game. Of course, everything is much more serious, and they have to adhere to the doctrine, but they are using keyboard and mouse as any player of the first-person shooter on a PC would do. But then, of course, come more complicated scenarios and more complicated machinery that you want to train with. So you come to joysticks, steering wheels, of course, and then you start to really use very bespoke controllers. We are integrating with pieces of hardware that are one-to-one replicating what you would have in your hands inside a tank. It has all the buttons, all the sounds, and all the feeling that you would have as if you would be sitting in the tank. So there is a lot of different peripherals. You can actually use a simulated binoculars into which we are actually sending the picture. So you are using you are using a real life device that looks like real life binoculars, but inside you see the image from our engine. So these are kind of things that we integrate with. On the side of the VR and AR devices, we are working with those for many years now, since the first Oculus, not the CV1, the previous ones, the development kits were released. We worked with them. And we are not having only access, of course, to the ones that you can buy off the shelf. We are working with different companies that are producing headsets that you normally can't buy because they're, of course, very expensive, but they're also very much superior to what you can buy off the shelf.
Let's now talk about team. And I'm really interested in two things. The first is testing. Testing is hard. In this case, I really cannot imagine how you test. Can you talk about that? How do you know what you're building is actually, going to work?
I agree that it's a very complicated thing. And I think we have it a bit similar with the games. We rely a lot on manual testing. So on the other hand, we have also one advantage. We have a requirements from our customers. Our customers tell us what they want to train. If they tell us, hey, I would like to train parachuting, they tell us what they expect from the training. So we, of course, put it into requirements, we put it into test cases, and then we turn these requirements to test cases. And then there's a lot of manual testing being done on those test cases, making sure that the functionality works. Where it starts to be really complicated, and that is also, again, like very specific, I think, for what we're doing, any new functionality has to also work with all the old functionality, all the previous functionality. And anything we change have to be also backwards compatible with all the data that were used for the previous functionality. So we have to keep a lot of the old code in to support previous functionality, previous type of data, previous ways of interaction. So that, of course, creates immense effort when we want to test our software. It's just almost impossible. We have to be always very thorough on, if we're delivering a new release, on testing, doing this, we call it regression testing, trying to find out as many things as possible that actually regressed from the last time we have had a release. We have a suite of automated tests. You can, of course, automate some of the things. I don't know, you can automate testing of artificial intelligence. If you give it some waypoint, if it gets there, if it shoots someone, if it can aim and shoot someone. But a lot of the stuff really needs a manual testing and a very, very skilled quality assurance people. So, for example, for us, when we hire a new tester, it takes several months before that person can actually deliver a quality results, because it is so complicated and there is so much of knowledge that needs to be put into it when you're testing our software.
Okay. Two of my takeaways from that was that it's really, really important to get the requirements correctly. And the second was that in spite of all that, it does take time for the QA folks to really start, doing a close to a perfect job as you require. What about UX designers? How do they then model the personas, and how do they get started? And what is the role of product management here?
Mm-hmm. So for the UX designers, we have started several years ago. We have basically found out that we really need to do something on the UX side. So we have UX designers in our team, because our customers sometimes are the procurement company. So sometimes we do not have access to the end users, but in many cases we do. We have access to the actual soldiers. So we can ask them what they expect, or we have access to the people who will use our software to train their soldiers. So we ask them what they expect from what we are delivering them, how they think that it should operate. We give them some kind of options, and we try to work with them as much as we can in this kind of agile approach to achieving the goal. So we constantly try to talk to them and find out what their opinion on the latest iteration is. That's the best case. Sometimes, as I said, we do not have access to the end users, and then we use our internal people. We have people who served in the military previously. We have people who have experience training in the military training centers. We have people who worked as administrators of a simulation training facilities. So we can talk to those, and we usually try to get the best UX design hints from them. As for product management, it's, of course, very important for us to somehow keep the products going into the future in one consistent and coherent way. That's a massive job, because we are having a lot of projects. Is another, I think, difference between the simulations and the games, where in the game you usually really focus on one game, maybe with a big team, but the team has one focus on this one game. We have 20 different projects for 20 different customers. They want different ways of, they want different new ways of using our software for training. And that's where product management has to look at all of these and kind of say, okay, we need to just shape this one a bit more so it also serves more of our customers, not only this specific customer. So that's the role of product management, making sure that what we're doing is reusable for as many of our customers as possible, not to do some bespoke development for only one specific customer.
On the same lines, what about the customers? How do they measure ROI?
That's a really complicated question because, of course, our customers use our software to train the soldiers. And it's sometimes very hard to find out exactly immediately if what they're using, if the training has a good outcome. You have to train a lot and very often to just get some of the skills. So we definitely talk to our customers. They are giving us feedback. Sometimes we find out that some of the procedures that are being simulated are maybe too complicated, or the peripherals are not delivering as much training as they should. But mostly we have a good feedback, and the most precious feedback is in the form of our customers telling us that because their soldiers were trained using our simulator, then they got away from some very, very difficult situations in real world scenarios. And we really had a feedback from a military personnel who told us that because the soldiers spent time training on our software, they then were able to react in a situation so that they saved their lives. So that is one of very nice feedback that sometimes we get. But really, measuring ROI is pretty complex on our software.
I mean, saving lives is priceless. So, thanks for sharing that. So we'll talk a little bit later in the show about two topics. You mentioned whole world simulation. So that sounds like an area of research. And of course, VR and motion tracking. But before we get to that, I wanted to talk to you and see if we can work through an example. Let's talk about, let's say, the simulation for parallel parking. If I was a developer who wanted to create this, how would I go about it? What are my options? How would I start?
So if you, as a developer, as someone who's sitting at home and trying to think about how to do this, I guess the fastest thing really is to get Unreal or Unity or one of these engines. And if you really only want to simulate or create a simulator of parallel parking and nothing more, it might be pretty simple using these systems to do that. You would just basically place two boxes somewhere. You would maybe use the basic physics that comes with these engines and the basic car simulation that is there. And you would place two boxes in some distance from each other. And then the player can just jump into the car and try to park and see if the player hits something or not. That would be your simple solution for that. Of course, things start to be more complicated if more requirements come in. You don't want to only just train the person to parallel park in a very artificially created environment. You maybe want them to learn how to park in the slope or when they're in the slope, or you want to train them to parallel park when there's a traffic around them. And maybe you want to train them how to parallel park big cars and small cars and cars with a trailer. And the more you want to train, the more you actually are starting to find out that it's more and more complex to make all the new requirements to work together. And that's where you start to think about, maybe I should start to look for a simulation engine, a simulation solution that would help me fulfill all of these requirements without me having to spend so much time on it. So to answer your question simply, if you want to do it yourself, definitely maybe get Unity or Unreal, which are for free, and you can quickly do something simple yourself. But if you're an organization who, for some reason, needs to teach their people or some other people to parallel park or in different situations and with different constraints, maybe try to look first if there is any solution that would deliver you the training already out of box.
I do want to dig in a little bit more there. You mentioned that one of the things you're looking for is, hey, do I hit something? But, as I'm thinking about this, What I really want to know is, am I steering correctly? Is my car sliding well into the slot?
So you can probably approach it from different angles and create different levels of complex solutions. So the most easy one would be probably that you would create some kind of 2D simulation where the player would be just operating with the arrows, a box, or maybe something in the shape of a top-down shape of a car. And you maybe know these hints which say that you should park next to the car in front of you and then go backwards until you are half with the car backwards, then start to turn. And you can maybe visually, you can have the player to just basically turn the car with the keys and with the keys on the keyboard and show visually when to do things, when to just start to turn and when to stop turning. So that would be the most simple thing, and you can definitely do that in the Unity very easily with the 2D engine which is there, I think, without any additional modules you would need. You then want to maybe do it a bit more immersive or a bit more, again, real life like. So you would want to do it in 3D, basically placing the player into the car. And again, you can do it so that the game is being operated by a keyboard and a mouse, where you can maybe with some keys, with the keys you can operate the car, and with the mouse you can operate the head. And in that case, you would just basically be able to operate your head and look behind you and see where you are next to the car in front of you. And again, you can provide some kind of hints in the 3D saying, now go backwards, and now stop. Now start to turn the wheel, and you would turn the wheel either with the steering wheel that you would have or with the keyboard. And again, the simulation can tell you, hey, stop. Now start to back again and stop. And now change the turn of the wheel. So you can do that. Again, if you want to do this kind of a simple thing with not too complicated environment, just maybe showing some simple approximation of a street and of the cars that you park in between, you would be able to do it in Unreal and Unity very simply and without any too many additions. I'm not sure about like the basic physics that is in part of the sandboxes, but maybe you would be even good with that. And then you want to go a bit more further. As you said, VR, you want to immerse the person even more. And of course, with the VR, you can have the 360 feel like freedom of moving your head and seeing basically everything around you. So that would create another additional layer of immersion. But for VR, you actually need much more believable world. So you would have to spend time on maybe creating a better interior of your car, and even the exterior. You would have to spend a bit more time on creating your virtual environment. So that would be a bit more work. You would have to create this 3D content. But on the technology side, again, I think it would be pretty possible to do with the standard Unreal or Unity engines, which now I think natively support VR headsets. But then it, again, would get a bit more complicated if you, as I was talking about previously, want to add more things in a different traffic, different types of cars, maybe different kind of slopes and conditions that you would need to do parallel parking. So that's where you would maybe need a bit more sophisticated physics to support different types of vehicles. You will need some kind of artificial intelligence module to create some pattern of life, traffic around you. And you might need support for more comprehensive controls, like even maybe a handbrake or something like that, or clutch, if you would have a manual gearbox. And that starts to be more and more complicated. And you would probably have to do some research on what kind of libraries exist for these engines, or you would have to build them yourself. So really, it all depends on how far you want to go and how broadly you want to handle this training scenario of parallel parking.
Okay, so start with Unity. That's a perfectly good place to start.
Mm-hmm.
But then as you make the scenarios more complex, you would need to specialize or replace the physics engine, the AI modules, and the support for additional controls.
Yes, the more you want to cover with your training, the more you will very probably find that the basic libraries or components that are available there for Unity or Unreal, that they are not good enough for what you want to achieve.
Okay, that's a good introduction. Now let's go back to what I hinted we would want to talk about, areas of research. Let's start with the whole world simulation. So you said that was an important addition that you guys have been working on at BI Sim. So a basic question, how do you do that? How do you make a replica of the whole real world using flat images?
So it's definitely not easy. It took us, I don't know, 7 years or how much to actually come with an engine that we're now using for the production. So basically, of course, there are data that you can use. There are satellite images. There are now OpenStreetMap data which you can access and get, and all that data is actually georeferenced. So from OpenStreetMap, you can get vectors that are representing streets or building or footprints of buildings in the real world coordinates. So you can actually place them there where they should be. The complex thing is how to get all the data into the memory of a PC so that it looks as good as it can and it still performs very well. That's the biggest challenge there. How do you represent the whole world terrain geometry in the memory? How do you represent it so that you can actually fit it into the memory, like in the places where you want to create a training? So there are many, many sophisticated algorithms for that are, of course, around the area of level of detail loading, where we had to just basically create some bespoke algorithms to cope with that. Of course, we are not having all the data at once in the memory. We're very cleverly streaming the data in there where you want to have the image from. We also, like, you can again get a data which represent the height map, or the basically how high things are in the real world, how high above the sea they are. You can get the data that they are publicly accessible, or you can buy them in a different types of precision. Again, maybe you get to a precision of 1 meter or maybe 10 meters. That data is maybe even publicly accessible or kind of cheap. But if you want to get into the precision of millimeters, then again, the data might not even exist. And if they would exist, they would be very, very, very expensive. So again, we had to come up with algorithms that we call the process refinement, refine the data that we have, maybe 10 meter precision. So you only have a basically vertex every 10 meters. So you can't, for example, do trenches or something like that, or ditches, because you would have to do only ditches that are 10 meter wide. So we're coming with these algorithms for refinement of the terrain so that we can go on the centimeter precision, and that allows us to do very, very refined modifications to the terrain in case our customers want to do build some trenches or want to have a very specific representation or very real life specification of the terrain. So that is the biggest challenge: how to get all of the data, how to store it so that it is very quickly accessible, and then when you access it, how to put it into the memory so it can be displayed in a very efficient way. So you still have 100 FPS, 120 frames per second when you're moving through the environment as you have in the normal games.
It's really fascinating, and I can imagine really, really challenging. What about motion tracking for VR? I imagine that's absolutely critical for realistic simulations as well. Can we talk a little bit about that?
When I hear motion tracking, I kind of think about this complicated tracking of all your joints and all your limbs and your head. We do not have to get that complex most of the times. We have customers who want that, who want to just basically track the motion of the soldiers, and we provide solutions for that. For the VR, it's actually not that complex because the headsets usually come with their inbuilt ways of tracking the motion of the head. They also come with very clever algorithms to prevent people from getting motion sick if the screen is not updating as quickly as possible. So that kind of a tracking of the head for the VR headsets is not that much of a complication for us, because the headsets usually come up with a good SDKs that provide us all the information that we need.
let's start to wrap up now. Is there any topic that you want to talk about that we haven't touched on today?
Not specifically. I hope that the session somehow is able to deliver the message that simulations are different to games. Even if we started with a gaming engine, we are now really, really very different to what a game would be. On the other hand, as I already said, if you would probably see some of our customers training their soldiers somewhere in a facility, you would get there and they would be sitting there using their keyboard and mouse, and you would say, well, they're playing a game. Then you would have to observe what is happening around that. You might think that they're playing a game, but everything has a really very strict rules. And for us, it's very important to not deliver a negative training. And that's what we do. That's what we try to achieve, to make something that really delivers a very, very good training. So anyone who is using our software is then getting out prepared for what can be ahead of them in the real world. So I would say that the biggest difference, if we should talk about, if I should close on the topic of difference between a game engine, as I described it at the start, and the full simulation engine, it's the vast amount of work that is being spent on the simulation engine so it can deliver the training that it needs to.
I did watch some of the videos of BI Sim on the YouTube channel, and I did find them fascinating. Leveraging all the efforts and all the success that gaming engine has done and channeling that into training, it is definitely something that I hope our listeners find as interesting as I did and talking to you today as well. How can people contact you?
So people can contact me on my email address if they want to contact me. It's a simple otakar.nieder@bisimulations.com. They can, of course, go to our webpage and contact our company through some of the contacts that I mentioned there. That might be the best way because, of course, I'm a bit busy, so I might not be just answering quickly. So I think the best way would be to go to our web pages, which is bisimulations.com, and search for the contacts information there.
We'll put a link to that in the show notes. Thank you so much for being with us today, Otakar. It was an awesome session. Thank you.
Thank you for inviting me, and thank you for your great questions.
This is Kanchan Shringi for Software Engineering Radio. Thanks for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.